All right, in this video we're going to practice a little more with that Lagrange error bound and finding the value of m. So we're going to start with this problem. We're going to find a fourth order Taylor polynomial for cosine x, and we're going to use that to approximate the cosine of 3. I'm going to have you do that on your own, and we'll come back and do the Lagrange error bound together. But I want you to think about the fact that does not mean this is going to be centered about 0. This is a Taylor polynomial. So find a convenient point that's close to 3 so we can be a little bit more accurate. Go give it a shot. Okay, since we're looking for the fourth order Taylor polynomial, I'm going to go out to the fourth derivative. So first of all, I'm going to use pi also as my center because pi is close to 3. I want to be as accurate as possible. So I'm going to evaluate f of pi. That's the cosine of pi, which is -1. F prime of pi, the derivative of cosine, is negative sine of pi, which is 0. F, the second derivative at pi, so the second derivative the derivative of negative sine is negative cosine of pi. Negative cosine pi is +1. Third derivative at pi, the derivative of negative cosine is positive sine, and that's 0. And then finally, the fourth derivative at pi, the derivative of sine is cosine pi, -1. So I'm going to use this to write my Taylor polynomial. F of x is going to be approximately this fourth order polynomial, which is equal to the first term, that's -1. The second term was 0, so that one's gone. Now the second derivative is +1, so this is 1 over 2 factorial x minus pi squared. The third term is gone because the derivative was 0, and then we've got the fourth term, which is -1 over 4 factorial times x minus pi to the fourth. This one's going to be a little bit cheap because we're going to actually use a calculator, but we're not going to use the graphing part of the calculator. I'm just going to use the scientific part of the calculator because I'm going to use it now to estimate pi. 3. I'm going to plug 3 into this function now, or this polynomial, to estimate the cosine of 3. So I'll plug 3 into this, and when I plug 3 into this, it's going to be important that you do use a calculator, because when I tried this the first time and I just used 0.14, that wasn't accurate enough, because we were pretty accurate when we chose the point to center this around. So we need to be really careful that everything is being calculated exact. So I know it's kind of cheap because we're trying to do all of this without a calculator, but I'm going to do this with a calculator. So I'm putting it into my calculator. I hope you've done the same. And I'm actually using the pi button on my calculator. You should have done the same. If you haven't, I'd recommend you go try that again. So then 1 divided by 4 factorial, which is 24, and then 3 minus pi to the 4th power. I got approximately, so the cosine of 3 is approximately -0.98999. I'm putting as many decimals as possible because remember, we're pretty close. We have a few terms here. We've gone out to 4 derivatives, and we've chosen a value to center this around that's also really close to 3. So we're probably pretty close to the actual cosine of 3. I mean, I guess I can just find that while I'm talking about it right now. So the cosine of 3 actual is approximately -0.98999,24966. So we're really, really close. That means our error bound is going to be minuscule. So let's find that Lagrange error bound. All right, so the Lagrange error bound says, in order to find the remainder of this fourth order polynomial, when plugging in 3, we know it will be less than or equal to, and we'll find m in a moment, the next term. So the next term would be the 4 plus 1 factorial. X is what we plugged in, minus what we centered around, to the 4 plus 1 power. Okay, if we simplify this a little bit, it's going to get kind of weird, but we've got m over 5 factorial. I should know that, but for some reason I'm drawing a blank. 5 factorial is 120, of course. And then 0.14 to the 5th power is something really small. And then I'm going to divide that by 120 because this is m times 0.14159 to the 5th, and then divided by 120. I'm just going to leave m as it is. So actually, I'm going to leave it like this. This is going to be good enough for right now. So here I am. I've got this. Here's my remainder. And this is a cosine function. Let's look at what the 5th derivative would be. So the 5th derivative, because that's what m is going to be, the 5th derivative of x, the 4th derivative was cosine, so the 5th derivative is going to be negative sine. And just like we talked about before, using sine and cosine, we're going to be pretty safe here and just use 1 for m, because we know that 1 will definitely be the greatest value of that 5th derivative. And that's what we're looking for. We're looking for the upper bound. We're looking for something that is definitely going to be greater than the actual remainder. So I'm going to use 1 for m. Okay? I'm going to guess you'll have more questions about this in class, and if not, if this is working for you, awesome. So m is 1. I'm going to leave this as 3 minus pi to the 5th to keep it exact over 120. If I calculate that mess, then I'm going to divide that by 120. So 3 minus pi to the 5th power divided by 120. So I got, in scientific notation, I got that the remainder will be less than or equal to, and I'm going to take it out of scientific notation, negative 0.123456474 266,401. Pretty darn accurate. So we're saying even though we're like estimating all of these things, like we said, m is 1, like, I don't know, because that's the highest sine could go, we're still so close to being the exact. So when we talk about the error bound, we're going to say, all right, we're going to take what our estimate was, negative 0.9899925,078, and I'm going to subtract 0.00123456474266, and I know that the cosine of 3 is going to be between that value and negative, this is going to be hard, I'm going to have to write it on the next line, negative 0.9899925,078 plus that remainder, 123456474266401. This is our error bound, and without just boring you with me putting all of this into my calculator, we would actually combine those together to say this is the lower bound and this is the upper bound. So we know that the cosine of 3 will be somewhere between those two values. Okay, that's the first example. Let's do a second one. There are 3 parts to this one. We're going to use the 3rd degree Maclaurin polynomial for e to the x to approximate the square root of e. And what is the error bound? I want you to try both the first part and the second part this time, and then come back. Okay, let's do this together. We know that since this is a Maclaurin polynomial, we know f of x. We know the Maclaurin polynomial for e to the x, and this is a 3rd degree. And in this case, that's also the 3rd order. So we've got 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, the square root of e, or e to the 1/2, is going to be approximately this third degree polynomial at 1/2. 1 plus 1/2 plus 1/2 squared over 2 factorial, which is 2, plus 1/2 cubed over 3 factorial, which is 6. If I simplify this just a little bit, I get 1 plus 1/2. 1/2 squared is 1/4. 1/4 divided by 2 is 1/8. 1/2 cubed is 1/8. 1/8 divided by 6 is 1/48. If I get a common denominator, then e to the 1/2 is approximately 48 over 48 plus 24 over 48 plus 6 over 48 plus 1 over 48. So if I add those, 48, 68, 72, 79 over 48 is approximately what e to the 1/2 is going to be. So here's our approximation using the Maclaurin polynomial. Now let's figure out how far off we might be. Okay, the error bound. We're going to find the remainder for this third degree or third order polynomial at 1/2. We know it will be less than or equal to m over 3 plus 1 factorial times 1/2 minus 0, because we centered at 0, 3 plus 1. All right, 1/2, well, let's do 3 plus 1 factorial. 4 factorial is 24. So we've got m over 24, and then 1/2 to the 4th is 1/16. So to save me some space, I know that our error is going to be less than m over 384. Okay, now let's talk about m. We want some value that is greater than the next derivative. So in our case, we're looking at the 4th derivative. And since the function is e to the x, we know that the 4th derivative of this will also be e to the x. Okay, so I know that the square, I know e is approximately 2.71828. The square root of e is definitely less than 2. So I'm going to use 2 for my value of m, because m is greater than that e to the 1/2. So it's greater than what it is we're trying to evaluate. I'm just going to let m equals 2. You can let m equal 3 if you want. You can let m equal 4, but that's not a very confident interval. But you can. We're making an estimate here. I know that the square root of e will be less than 2, so I'm going to let m be 2 because I know that 2 is greater than that remainder. It's greater than that next derivative. All right, so if I let m equal 2, then I know that the remainder will be less than 2 over 384. The error bound then would be 79 over 48 minus that value, which is 1 over 192. And it'll be greater than that, but less than 79 over 48 plus 1 over 192. All right, if we do some calculations then, 79 divided by 48. I'm going to actually do the calculations here because these aren't very big. 1.640625. And then 79 over 48 plus 1 over 192 is about 1.651041667. Notice I'm writing all of the decimals because we're trying to be exact here. And then if I actually find the square root of e, it's 1.6487. So I was right. We were in that bounds for sure. So we're saying, based off of all of our estimations, based off of all of our best guesses, our convenient values that we chose, we're pretty confident with our answer. We're saying that our answer for the square root of e is somewhere between those two numbers. And that's pretty close, depending upon what you're doing. Okay, now comes something a little annoying, tedious, but also kind of useful. What we're saying is, what degree polynomial is guaranteed to give an error that is less than 0.001? So what we're saying is, we want this error of some n value, so some degree. If we plug in 1/2, we want that error to be less than or equal to 0.001. Well, the error I know is m, some m value. Let's use the same m because it's still 1/2 that we're plugging in. So I'm going to still use 2 for m. We don't know n this time though, so it's n plus 1 factorial. We are still plugging in 1/2. We are still centered around 0. We just don't know this power. And we want all of this to be less than or equal to 0.001. So let's do some simplifying first. We've got 2 over n plus 1 factorial. This is 1/2 to the n plus 1. I can break that up into 1/2 to the n times 1/2 to the first because of the exponent rule. And I know now that this 2 times this 1/2 will just be 1. So really what I'm looking for then is 1 over 2 to the n times n plus 1 factorial. I want this to be less than or equal to 0.001, or 1 over 1,000. And this is really annoying, I know, but we're going to guess and check. So let's try plugging in 2 for n. We just want to make sure that this fraction is less than 1 over 1,000. So as long as we can get a denominator greater than 1,000, we're good. And we want the one that's closest. We don't want to have to work too hard at this. So I'm going to try 2. 2 squared, that's 4. I'll just put that here to save me some space. And then 2 plus 1 factorial, that's 6. So 1 over 24 is definitely not less than 1 over 1,000. We need a denominator bigger than 1,000 in order for the fraction to be smaller. So let's try n equal 3. Okay, 2 cubed, that's 8. 2 cubed, that's 8. 3 plus 1 factorial, so 4 factorial is 24. 8 times 24 is only 160. Not big enough. Let's try n equals 4. 2 times 2 times 2 times 2, that's 16. 5 factorial is 120. And there it is, because 10 times 120 is 1,200. So I know that a 4th degree polynomial, sorry, the music just started outside, will guarantee an error less than 0.001.